Talking about coronal hole seismology.
Hello everyone. So I'm Aneta and I work in the Leibniz Institute for Astrophysics in Potsdam. And maybe this title is a little bit, promising, but actually this is the direction that I am heading to. This is like ongoing work, so maybe the results are a bit preliminary. Of course, we already heard today, so Richard was mentioning a lot about waves and also Raoul about coronal holes. So we know that the corona is highly inhomogeneous, and actually coronal hole is a temporary and large region of relatively cool, less dense plasma in the solar corona. And the average magnetic field strength of coronal holes lies between 1 and 7 Gauss. And what is the most important that those kind of features are characterized by open magnetic field lines, and that the strongest solar wind originates exactly from the area of coronal holes, what is kind of interesting. And so we have a measurement of one specific coronal hole measured at the 30th of April 2021. And this was measured by several instruments, but I will be showing you only like my part of this work. So of course we were interested in interpolation of magnetic field for this feature. So we used the potential field source surface PFSS extrapolation, but also we wanted to go to the like more closer view of this region. We also used the data from HMI and derived the magnetic field components using also PFSS with a finite difference scheme. And this was actually done by one of my collaborators, Stefan Heinemann. So we assume that potential force-free magnetic field of the sun, which is known to be crude approximation. So the source surface haze was set to 1.7 solar radii, and the lowest end of the values uses 2.5 solar radii. And here I'm showing you only the open magnetic field lines because otherwise it gets too messy here. And here you can have also the scaling of the magnetic field. And our coronal hole is placed over here. So you can see how this looks like on the intensity image from AIA and our extrapolation. But this kind of study was done because I was just curious what kind of results we can obtain. And as you know, AIA doesn't have a possibility to measure Doppler velocities, which is kind of challenging to tell about the oscillations without velocity information. But our goal is to investigate the roots of the coronal hole using plasma oscillations at a different level of the solar atmosphere. So we thought that maybe it would be worth to kind of normalize our data to avoid this kind of difference in intensity, because obviously this is visible in the corona, but using, let's say, Fourier methods, we can have a strong correlation between intensity and power spectra. So we used kind of new developed time normalization to emphasize minor brightness variation in a contrast between a temporal set of preceding and following images. And what it does is measure brightness in specific spatial locations, so it's target, across temporal set. And then this temporal set is both preceding and following images around the target image. So here, the temporal set in all data processed here is to be about plus minus 10 images. So every pixel is a temporal set and is processed via very simple formula. So after this kind of normalization with some threshold, we obtained a processed signal. And I will show you how does it look like for the data. So basically we have the same data. So on the left panel is original from SDO-AIA at 193 angstrom, and on the right, you have the normalized one. So basically what it does is the same data set, and you can see that on the left side, the motions of the plasma are pretty much visible, whereas on the left side, we don't see really much movement in there. So we thought that maybe this could give us some signal in a Fourier transform, because we are interested actually how does it oscillate around the coronal hole, and what is the distribution of oscillation, spatial distribution of the oscillation. So I calculated the Fourier transform and then inverted it, divided into some frequency bands and inverted it back. So to get like a power maps for some given frequency ranges. And we can see that coronal hole, even on the normalized data, when you don't have like really high intensity difference between this area, is still visible. So this leads us to the idea that it might be some means to estimate boundaries of the coronal hole, which might be then useful also to my colleagues then later on in the later analysis. But I was also interested in particular oscillation. So I thought that maybe it would be worth to set up some boxes and just measuring how the plasma is behaving in this location. So here, again, on the left-hand side, you have the original data, and on the right-hand side, you have the time normalized AIA and 193 angstrom. We did this also for the different filtergrams, but I'm presenting here only one. So I did a kind of very, very simple time-space plot. So just we are just investigating how the plasma is moving over the time. And we can identify some oscillation, but this is quite not so accurate. We would have to, I don't know, like fit some, make some fitting on it to really identify that. But there is like some more simple method to actually do it, which called Wavelet. And this is based on the Torrance and Compo method, which was published in 1998 already. So as you can see, for the original data, we have a lot of signal here, but actually we can detect some kind of 3 to 5 minutes oscillation here. And excuse me, but this is like kind of other way around. It should be like this, but my IDL refuses to do such a plot. So actually, what you see, these two samples are this set of plots. So for the original data, you can see that we have less signal, and we can detect less oscillation than for the normalized one, which is kind of interesting. And here also we can detect more stable oscillations in this area. So this what I'm showing here is with 95% of confidence. So we know that we can identify oscillation even based on the intensity data from SDO, which is kind of quite surprise, but it's nice to us. Okay, so why we want to use the UCoMP then in the future? Of course, we've heard already that UCoMP has a possibility to measure Doppler velocity and magnetic field in Coronal, and has a large field of view and larger spatial resolution than the COMP. But our main goal is kind of track the long-living coronal hole. So if we'll be having some maybe equatorial coronal hole, then maybe we can observe it at the limb, and then kind of track it over the solar disk, and then maybe go to the other limb. We don't know, but this is a kind of idea how to do it, and we know we are quite sure that these observations can bring us more information about the propagating waves inside this kind of features. Also, UCoMP can resolve fine structure of the plasma, which is kind of crucial in this kind of investigation. And maybe we will be also interested in a polar coronal holes. But but for now, we wanted to track like really equatorial long-living features, and we'll see what it will give us. But I think that this is very nice context data to our research. Yeah, and that was all. Thank you very much.
I didn't rush you in order to get to lunch, but lots of time for questions. Thank you.
So the coronal holes seen at the limb, I think that's a great idea.
Yeah.
One comment, actually, can you go back to that picture? It's the one I was going to comment on, your
Okay.
final slide?
Yeah.
No, your final slide.
Yeah.
That one. If it's a narrow coronal hole, you're going to have so much line of sight effect that it's going to be hard to see it.
Yes.
But like this one, you can see it's also got the very wide structure above it. And so that one you will be able to see pretty well you're looking at. And if you look in the azimuth, you can look at the expansion of the coronal hole, like the non-radial expansion of it in a way, which could be quite interesting.
Yeah. Exactly.
We don't have a lot of signal in the large coronal hole. Yeah. The data are known.
Yeah.
It's just the line is off. It's not much fun.
Yeah. So I just wonder if you can do simultaneously with EUI at a question.
Yeah, I was thinking about some joint observation or taking data from different instruments. Yeah, this is also the EUI has similar filtergrams as AIA. So yeah, we are thinking about to do this, but this is like ongoing work. So we are still experimenting, and it's just like kind of we were curious what we get, you know. So, but as we know that it can have some additional input to other data which we're taking for this event, this feature. So yeah, we will be trying everything what we have, including EUI. Yeah.
I'm just curious about the oscillations in AIA. Have you done any type of analysis to try to figure out if it's due to heating or density or?
No, not yet. I mean, like I did in the past, I did similar, let's say, investigation, but for the flares. But that time we had actually the full scan over the spectral line, so we could derive the Doppler velocities. So this is like kind of tricky, you know. With AIA is hard to say.
Any questions? All right, let's